Hello. Cool. Can we see my screen okay? All good? Wonderful. Hi, so my name's Steve Kench. I'm a PhD student from Imperial College, associated with the Faraday Institution. I'm going to be talking to you about machine learning for next-gen batteries. So the group that I come from is Sam Cooper's in the Dyson School of Engineering. And we're focused on how you can apply machine learning for, as Leah said, battery characterization and optimization. So this image over here is just an example of some of the stuff that we've done. So on the left is a real microstructure, and on the right is a synthetically generated microstructure. And I'll get onto how we produce these in a bit later on in the talk. So first of all, I just wanted to explain where we sit in terms of the scale and the structure of a battery, and also just briefly some machine learning approaches that can be applied at these different scales. So if we start off at the atomic scale, there's a lot of materials discovery work going on, looking at how we can try and predict and identify good potential new cathode and anode materials. And a lot of that is done through trying to predict electronic structure, electrical properties and chemical properties to try and identify these new materials. Then if we think on the opposite scale, up at the pack design level, a lot of the work at this scale in terms of machine learning is trying to predict how we can balance a battery. So what cells we want to draw charge from at a particular time in order to try and maximize range, minimize degradation, and try to get the most out of the battery over its lifetime that we can. And then down on the cell, one step down on the cell level, there's a lot of work on trying to predict state of health and state of charge of individual cells. So given some kind of charge profile, can we predict how many more cycles a cell will last for and how that behavior will change over time? But what we are interested in is the structural scale. And the reason this is so interesting for us is because structure really has, and microstructure in particular, has a really strong influence over electrochemical properties. So here we've got an example of a NMC cathode. Oh, that's pointing to the wrong place, that should be cathode. Of an NMC cathode, where we have three phases. So we've got the active material, which is gray. We've got the binder, which is white and holds those active material particles together. And then we've got a porous phase, which is the black. And so an example of how microstructural properties can affect behavior is that the surface area of this active material, so the gray, really strongly influences how easy it is for lithium to intercalate into the cathode. So the more surface area we have, the more available area there is for intercalation. But then on the counter side, we have the larger volume we have of NMC, the bigger our capacity, or to some extent affects the size of our capacity. So we have all of these different microstructural characteristics and properties that affect each other and interplay and have a very strong influence over the performance of our battery. And it's difficult to immediately say this is the best structure and this is the best structure overall. That's definitely not possible. But even to say this particular microstructure is best for some particular case is also a challenge. So trying to optimize and characterize these materials is essentially what our group focuses on. And the way we have been doing that so far is largely through this machine learning method called Generative Adversarial nets, which was developed by this guy in Goodfellow who worked for Google and now works for Apple. And he developed this with a very different goal of just trying to generate fake faces. So all of these faces on the left are artificially generated images. They essentially taught a neural net to produce these faces, given a massive set of real images of faces, and that learned to produce these fake faces. And so we're essentially taking those methods and applying them to materials. So before I go into what we've done in terms of that, a quick and the most common description of how a GANs works, I'm just going to go through it very briefly. So we can think of a GANs as being a two-player game, and one way to think of this is that we have this scenario where on the left we have a detective, and on the right we have a fraudster. And the fraudster is trying to make fake $50 bills. So he's trying to do, they are trying to do the best job they can to make these fake $50 bills. And the detective is doing the best job he can, or they can, to distinguish between the real and the fake bills. And as time goes on, the fraudster gets better and better at making fakes, and the detective gets better and better at telling the difference between fakes and reals. And so through that iterative process, we land up with a fraudster that can make very realistic looking $50 bills. And that's essentially how we get to the point where we have a GANs that can produce fake faces or fake images of microstructure through that two-player scenario where they fight against each other. And then at the end, we land with this generator that can just make these fake instances. So yeah, those two players are actually, instead of being these people, they're represented by neural nets that we make essentially fight against each other. That's where the adversarial bit of generative adversarial networks comes from. So we essentially, well, Andrea from our group took this method and has applied it to materials, and that was being recently published in a paper called Pause for Thought. Definitely worth having a look at. So I'm just briefly going to take you through some of the steps that we went through for that paper. So when we look instead of just at the general detective and fraudster, we can go into more depth and think about how we actually train one of these networks. So if we have a set of training images, in this case, we have this solid oxide fuel cell material, or SOFC, we might have a set of training instances, so examples of that microstructure. And we give those to the discriminator, which is, if you remember, playing the role of the detective. But then we also have a generator, which is playing the role of the fraudster. And over time, we go through that process that I described before, where we teach the discriminator to tell the difference between these real images and fake images. And we teach the generator to try and make more and more realistic fake images. So over time, both of these neural nets learn, and eventually at the end, the key thing is, again, we have this generator that can make really realistic fake images. So some examples of what we've applied this to, we've got lithium-ion, the lithium-ion cathode. This is all open source data, and an SOFC anode. We took training set examples. So you take that 3D training set and you take small crops, and those are your training data for your real samples. And then we train this generator, and eventually you get this generated set of images, which are visually indistinguishable. So you can see the top and the bottom, very similar features to the eye. And one of the fortunate things for us is that when you're generating faces, there's no real way of quantifying how good or bad those faces are, because it's just faces, right? So we don't really have properties of a face that we can check. But fortunately for us, when we're looking at materials, there's a ton of different metrics or properties that we could decide to try and analyze to say, how realistic is my generated set compared to my training set? Are there differences between these, or are they statistically the same? And so Andrea went through a bunch of different microstructural properties, which we essentially just select because they're important to us. We care about these electrochemical properties. So for example, we check phase volume fraction, where we generate maybe 100 instances of real and fake data. And we compare a property like phase volume fraction. So this is, if we generate 100, we take 100 crops of the training data, we get a mean and a standard deviation for that property in our training data. And then we do the same thing for our fake data, and we see how they compare. So how realistic is my microstructure in terms of the volume fraction for pore, is what this left-hand side is saying. How realistic is it in terms of NMC particle is in the middle? And you can see that the mean values align very well. We have some issues with the standard deviations in that we get a lot of clustering. So all of our fake samples tend to cluster around the mean volume fraction of whether that's pore or active material or binder. We get this clustering. And I'll talk about how we got around that a bit later. But in general, we get very good replication of features, our training data set, whether it's in phase volume fraction or surface area or relative diffusivity. So this is a measure of how much percolation there is through a microstructure. which is an important electrochemical feature, or triple phase boundary, which is where three phases, black, gray, and white, this is the points where all three phases meet. And triple phase boundary density asks how much does that happen? And we can see that across these four properties, our fake instances replicate our real data set relatively well. And another metric that we can look at is two-point correlation function, which I won't go into too much depth, but it's essentially a measure of the distribution of a phase. So how clustered is our phase, what kind of geometric shapes are there at different distances from a pixel. And again, we can see that the real sample, which is the solid line, and the synthetic samples, which are the dotted lines, are replicated relatively well. And this is considered a pretty good indicator of how real relation function matters. So these basically give us a tool where we trust relatively well that we can produce, oh, my internet connection is unstable, where that we have a tool where we can use fake instances of microstructure that look realistic. Just like those faces, we can make these new instances that look real. But that in itself is a really cool tool, but why is that useful? Why do we care about being able to generate more microstructure? Well, there are loads of different applications that I'm now going to go through, which are these different avenues that we've gone down for how we can apply this, this tool that we now have. So one really useful application is the generation of periodic boundaries. So what that means is that instead of generating just a normal instance of microstructure, we can enforce this constraint where we say the right-hand side has to match up with the left-hand side. So this top left is in the instance that we're actually talking about. But if we tile it across copy that instance 4 times and tile it, you can see that the boundaries line up. The left side lines up with the right. And the reason this is so useful is because when we're doing electrochemical simulations, boundary conditions are really important. So when we have mirror boundaries compared to when we have periodic boundaries, you can see that the periodic boundaries open up all of these possible paths. So you can see there's extra flow, there's like more flux over here and an increase in flux over here. And that's because we've opened these paths that can come in from out from the right and in through the left. And that's a much more realistic scenario. And on top of that, it means that we can use much smaller instances, because instead of under normal conditions, we have to worry about how these edges are affecting the behavior that we're seeing, because the edges are obviously a weird, like non-realistic feature of our simulation, where we're trying to represent a massive microstructure, but suddenly we have these strange boundaries on the edges. Whereas with periodicity, we've gotten rid of that, which means we don't have to use these huge volumes to try and negate the effect of edges. So that's one of the really useful things about using periodic boundaries. And yeah, so we can calculate tortuosity and other features using this approach. Another very brief but quite cool thing that we can do is generate huge data sets. So the original data set that this was trained on was a 250 by 250 cubed sample. So it's a 3D 250 cube sample. This volume that I produced here is 1,000 voxels cubed. So we can generate almost arbitrarily large sizes. And again, that can be useful for chemical simulation, where we necessarily even have to generate cubes. We can make long, like cuboids or any shape, really, any like cuboidal shape that you want, just by manipulating our generator after we've trained it. So those are some of the fundamental interesting uses that we started with. And I'm now going to talk about a kind of different avenue that we went down, which was a new approach. So these were kind of like applications and some extensions of GANs. This is a new approach where we're trying to solve a slightly different problem, which is so all of the previous work that I showed you was we were using 2D data to generate more 2D data, or we were using 3D data to generate more 3D data. Now, the challenge that I've been working on has been, can we use 2D data to generate 3D data? And this is like quite a long-standing challenge because it's hard to image things in 3D. That's the fundamental reason why we're interested in this. Or not even hard, but there are resolution limitations, there are field of view limitations with most 3D imaging techniques. So we want to try and image something in 2D and then take advantage of that excellent resolution that we have in that large field of view and project that into a statistically realistic 3D volume. And there are a lot of approaches already out there. So this is a long-standing challenge that people have already been interested in for a long time. And one of the most common approaches to it is to take a 2D image, try and extract some features. So for example, if we have grains, we might try and extract grain size distributions or do orientation analysis. And then using those statistical features that we've extracted, we'll try and reconstruct 3D volume. Our goal is to have a 3D volume that replicates those 2D features. Now, the main issue with this is that all of these statistical features that we extract lose information. There's an intrinsic loss of information. When you approximate a grain to a mean diameter or a distribution of diameters, you lose all of that geometric information about the shape of those grains, how the shape affects the maybe covariation between shape and orientation. So there's a lot of loss of information. So that's what the disadvantage of this particular approach. Then we have other approaches like two-point correlation analysis, where, as I spoke about earlier, the two-point correlation function is a good measure for how realistic a microstructure is. However, in this approach, we take a two-point correlation function and try and replicate it in 3D in exactly the same idea as before, where we measure something in 2D and try and replicate it in 3D. But again, there are issues with this approach, mostly based on the fact that this function is degenerate. So there's no unique mapping of a 2D micrograph to a two-point correlation function. There could be loads of different microstructures which have the same two-point correlation, but aren't necessarily realistic. So that's the downside of this approach. And so that essentially leads on to what I developed in terms of a GAN's approach to try and solve this problem. So SliceGAN is very similar to a normal GAN, except, at least for the start, in that we have some 2D data set. And we take some crops of that. So we take some crops out of that 2D data set, just like before. Now, the difference is that when we look at our generator, we have a 3D generator, which makes these 3D volumes. But because we can't directly compare 2D to 3D, what SliceGAN does, it's in the name, is take loads of slices of that 3D volume and then compares those to the 2D batch. So instead of, the fundamental point is that instead of trying to make a 3D volume that's realistic, we try to make a 3D volume that has realistic slices. And we hope that that will make a realistic 3D volume. And then we go through the same process of discrimination, backpropagation, and training our generator to make these realistic volumes. And so here are some examples of data sets that have come from this. So this is a separator. It actually was originally a 3D data set, but I just took a 2D slice and trained my GAN on that. And this is a synthetic volume that 3D volume that I trained just using, the slice is actually larger than this, I've just zoomed in on it, but just using one 2D slice of separator material. So you can see it looks pretty realistic. And yeah, so quite happy with these results. And one of the cool things is that you can see this material, it's like a layered material. And we can generate anisotropic materials just by making the slices on two directions look like this, and then the slice on the top look like so it looked like a different perpendicular training image. Sorry, that's a bit, yeah, it's quite hard to explain that without lots of drawings. So yeah, so this is an example of one of our 2D reconstructions. I've also done, this is a Perovskite KPFM where this is actually the full training image. So you don't need much data at all necessarily, especially when you have simple shapes or a simple geometry. So yeah, this again went from a single 2D image to this 3D instance. And again, I could produce as large an instance as you wanted in whatever shape you wanted. and it takes like a matter of less than seconds to produce. So for this, which is maybe 128 voxels cubed, it takes less than a second to generate one of these instances, which is quite impressive compared to most of the previous techniques that I showed you, which not only are less accurate, but also can take like hours or days to produce a single sample of this size. And then last of all, an example of SliceGAN. So this is the image from the first slide, sorry, an example of lithium-ion cathode. So this is an image from the first slide, where on the left, this is the full training data set, a 250 cubed voxel training set. And on the right, I've produced a synthetic volume of the same size, where all I used was a single slice from this initial volume to train a generator to make this. So again, you can see visually indistinguishable features. We've gone from 2D to 3D, so it's very promising. And again, one of the nice things about this is that we don't just have to say it looks visually indistinguishable. We can take the same metrics that we used as before, calculate them and say, this is exactly how realistic it is. So I'll go through the same metrics as before. We have volume fraction, where this time I'm comparing 3 different sets of microstructure, where again, the left-hand side is real. The middle is the 3D to 3D that I was talking about before. And the right is 2D to 3D, so SliceGAN. And you'll see that the distribution of features is much more realistic, the standard deviation is much better when we compare real to synthetic. And that's because it's as simple as changing the nature of the loss function in our GANs. It made this massive improvement on how, these distribution of features. And yeah, that's kind of courtesy of all of this incredible work that's going on with from like the general GANs community, which like we just get to kind of take and then put into our work, and lots of stuff just works incredibly well because so much research has been put into this approach. So yeah, that was volume fraction. If we look at surface area, again, we have very good matching of these distributions with some outliers. Effective diffusivity is the same, and triple phase boundary density. So again, we're producing realistic samples, and this time just from a single 2D slice instance, we can produce realistic 3D samples. Okay, so I've spoken about how we can produce realistic instances. I've spoken about how we can go from 2D instances to 3D instances, but that itself again is just, these are tools that are useful. But we want to be able to do something with that microstructure. What I was speaking about at the start was how can we optimize microstructure? How can we explore a space? We don't want to just be generating more of the same stuff. We want to be looking for the best possible microstructure that we can find within that possible space of microstructures. So one way that we can do that is by latent space interpolation. So I'm going to show an example. This video shows essentially what latent space interpolation is, which is on a trained GAN. So this GAN was trained to produce faces. We can vary Z by very small increments. So we add some random number onto Z. Sorry, I should go back a step. Z is a random number, a random vector, which we input into a GAN that basically determines what the output face looks like. And so by varying our input Z, we also vary our output, the appearance of our output face. And this is an example of what happens when we randomly vary Z. So when we randomly vary Z, we get this random changes of face. And you can see also that the space is smooth. So what that means is that we get this smooth change in the appearance of these faces, because that mapping from Z to faces is it's a smooth mapping. But we don't want to randomly move through microstructure. We want to have a target and say, this is the type of microstructure that I want. Can I make it? Can I achieve it? And so instead of, oops, don't want to skip through. So instead of randomly moving through Zs, I've developed this way where we can change Z in an informed way. So if we start with some random Z, we generate an image, we fix the network weight. So our network's already trained. We don't have to worry about updating our generator anymore. Our fraudster's good at making fakes already. We don't have to worry about teaching him anymore. So we just want to update our input Z. So we get out this image and we can calculate a material property of that image, for example, volume fraction or surface area. And then we can update Z in an informed way to try and move that property towards something that we particularly want. So let's say, and that essentially is achieved in the form of a loss function, which is given by the difference in our target property versus the real property that we calculated. So the example I'm going to show you is if we have some target for our volume fraction of active materials. So gray is active material, again, and black is pore and white is binder. So if we have some target for our volume fraction, we can try and make a microstructure with that exact volume fraction. Now, making a single uniform volume fraction isn't necessarily that interesting. So what I've tried to do here is, instead of making a single volume fraction, I want a graded microstructure. So this left-hand box, my target volume fraction is 0.4 or 40% gray. This right-hand box, my target volume fraction is 50% gray. And then in between, we have this linear gradient. And by going through that iterative process, we can change our microstructure, change Zs that eventually we match that exact target that we set. This is, again, an incredibly fast process. It takes like less than 10 seconds to go through this whole linear, like this whole teaching process and iterative process. Now, there are some slight issues with this approach, and the main one is that our generator is unconstrained. It doesn't necessarily have to make realistic looking images anymore, which leads to these weird features like this non-circular feature, this hole that I have in my NMC particle, which isn't very realistic. But one way we can get around that is by adding an extra term into our loss function. So now I'm not just saying, generate me a sample that has this volume fraction. I'm saying, generate me a sample that has this volume fraction and gets a good score from my discriminator. So you not only have to match the volume fraction, but you also have to be realistic. And you can see that once we do that, the change is much smoother. Look at all these nice smooth circles, nice realistic looking NMC particles, and still a very, very good match for our target gradient. Just to be clear, this is actually a 3D volume. So we have 64 voxels down, 640 voxels across, and then there's also a depth of 64 voxels. So that's why it might not look like it's necessarily as graded as it actually is, because there's a volume, there's a depth aspect to this. And this is just to show close up exactly what's going on. So we have this growth. Some particles are essentially growing, some particles are shrinking, and that's how we achieve this particular volume fraction that we want. Okay, so this is all good and well when we know exactly what we want, right? If I have a target property of surface area and a target volume fraction, then this is great, because I can say, try and make me this instance, and then I can do electrochemical simulations and see how well it performs. But there's still an issue here, because I have to know what I want in order to make this work. I have to know that I want a microstructure with this volume fraction and this porosity, or this surface area. But it's not easy, as I said before, it's not easy to know what those optimum structures might be. So the final step of things that I'm going to present is, how can we let our generator loose and give it more variation, more option, and let our generator decide what's optimum. And in order to do this, we can't just use a single training image, because a single training image might have some variation, but realistically, so we might have some variation because if I take an instance here, I have a high porosity or a low porosity. Sorry, if I take an instance here, I have a high porosity. I'm very sorry for the changed colors of things. This is now, black is now particle, white is pore, and gray is binder. Terrible, terrible from me. So if we take an instance over here, we have high porosity. If we take an instance over there, we might have low porosity, but that's not really enough variation for us to explore the possible microstructural space. So instead of just using a single training image, we can use multiple training images, where here we have a low porosity, here we have a high porosity instance, and then we can change even more properties. So for example, here we have a high binding between our a high adhesion between our binder and our NMC particle. And just to say, these images are produced. So I've taken these images from Scott Roberts, who works at Sandia National Labs, and it takes him about a matter of a few days to a few weeks to produce one of these samples. So they're very computationally expensive to produce these synthetic images of microstructure. Yeah, so we can produce all of these microstructures with these different properties. And then one of the nice things that we can do then, sorry, a step before I show you the nice pictures, is that we might have a set of all of these, we might have a set of kind of corner cases where we have a very low porosity, low adhesion, or high porosity and low adhesion. And we have all of the extreme cases. And what we want to try and do is interpolate in between so that we can explore this space of and just so CA is carbon binder to active material adhesion, POR is porosity, and CC is binder to binder adhesion. And then there are a bunch of other properties that we can explore. It doesn't really matter particularly what they are. We can basically use any property metric that you want from your training images. And once you've trained a GAN with those specific images, we can then do this really cool thing where we interpolate in between. So I'll just pause very quickly there. So essentially what we've done is gone from, we start with this particular image that has low porosity, it has low carbon active binding, it has low carbon binding, and depth is just because it's a 3D image and I'm starting at the very top. We then can raise porosity and literally, can we? We can then raise the porosity, and this is real-time generation. So you remember I said that it takes days to generate a normal instance of this. This takes like sub-seconds to generate new instances. Every time I move that clicker one step, it's real-time generating a new instance of microstructure. And we can what's even cooler is that you can see this interpolation between properties where we were only taught on low porosity and high porosity, but my generator understands how to interpolate between all of those properties and how to reduce that increased porosity as we go along there. And then the next cool thing that we can change is the binding strength between gray and black. So as we increase that, you see that in this final image, suddenly we have this collection, this like cohesion of binder around our NMC particles, where the binder tends to stick, and that's realistic. If we compare that to our training image, I can't zoom in, but if we compare that to these training images, you can see, actually I can, you can see that the high binder caused exactly this to happen, but the nice thing is we can interpolate all the possible structures in between. And yeah, so this allows us to explore these properties very rapidly. We can just generate new samples with whatever properties we want, with a smooth interpolation. And I think the last thing it's going to show is what happens. Okay, so WT is loading strength, so how strongly your microstructure was crushed during processing, and then depth is just looking through our 3D volume. So just to see that this whole thing is realistic and it is 3D. And this is the speed at which we produce new volumes. It's literally a click of a button and we have a completely new realistic microstructure. Okay, so in conclusion, we can do a bunch of cool things with GANs. We can make statistically realistic microstructure from a training set. We can make crazily large volumes, as many instances as you want, and you can impose periodic boundaries, loads of useful tools for simulation. We don't have to have 3D data. We can go from 2D to 3D data. If you have a nice, clean 2D representative 2D training image, you can make a 3D volume from that. We can explore microstructural space. If you want to make one particular type of microstructure with some features that you already know, then we can do that. So we can say, we can explore in an informed way, or we can interpolate between microstructures randomly to try and explore and find new microstructure. And this last one will probably be linked in the future to some kind of optimization approach where we try and put this into a closed loop where we have some kind of calculation that informs how we try to pick our properties. And those will also be linked to manufacturing conditions. So we have this really nice closed loop where we can generate a structure, see how well it performs, and then try and generate something better and just go round in that loop until we have something optimum, hopefully linked to manufacturing conditions. So that's all from me. Thank you very much for listening. And I think there's one question already in the chat. So I will read that out. Ooh. I don't seem to have access to the, oh, cool. It was just a thing. So, okay. Yeah. So if there's any questions, let me just pop them in the chat.
Hi, are you able to see the questions in the question and answer section? Just wanted to check.
I think so. I'm not sure there are any questions currently.
So I think I have one from Myla Chauffeur, and it says they just wanted to check that the fake microstructures are derived from only image analysis of real structures, i.e. the parameters are not inputs to the faking step, so are independent validation of the match quality. Have you compared more complex functional properties for real and fake structures in appropriate models, e.g. for electronic, ionic, conductivity, mechanics, or whatever?
Yeah, so no, the structures, the properties are not, so at least in all of these images, the properties, great question, by the way. The properties are not inputs in all of these examples. In any of these cases, sorry, I've got to get back to where we were. In none of these cases are properties an input. They're just something that we test afterwards. The only input is the images themselves and instances of the images. Now, when it comes to the interpolation step, we have to have particular properties as inputs. So for example, porosity, all of the properties that we're trying to explore, like porosity or binding strength, have to be inputs, because we're trying to learn how a property, we're trying to learn the link between property and structure. So you need to have those labels put in there, but for all of the previous ones, no, they're not. In terms of more complex electrochemical simulations, the reason we're using effective diffusivity is because it's very fast, as we said before. It is generally a good measure of performance. The reason we're not doing more electrochemical simulation is just that it would be time consuming, but I think that is definitely a step for the future. And I know that for these cases, we're going to be doing, for these examples, we will be doing for electrochemical simulation in the future. I'm afraid I can't see the questions there, so.
That's fine, I can read them out. So we've got one from Sam Cooper, and he says, fantastic talk, Steve. What do you think the limitations are for the generative adversarial network approach?
That's a biased comment from Sam Cooper. I think the limitations at the moment are, one limitation is definitely resolution. In terms of like the size of 3D images that we can generate are just, our networks are limited in terms of memory. So if you have a very high resolution 2D image, we can only go so far in terms of what we can capture. Often you have to downscale in order to make this work, but that is something that we will try and get around in the future. Other limitations, there are particular limitations around geometry. So for example, it's really hard to make perfect circles. And that's like an issue with long range dependencies. It's hard for one side of a circle to talk very coherently to the other side of a circle and say, we need to be round, or we need to be perfectly round with this curvature. So those are two, I would say those are two of the key limitations we've come across, is long range features and like resolution, which is just a computational limit, which we'll get around eventually. Yep.
So we've got another question from Milo. It says, how confident are we that the interpolated microstructures are actually experimentally accessible? Or conversely, that a useful optimum lies within the interpolated range?
Absolutely, great question. The first question about how confident we are about how realistic the interpolation is with respect to experiment, the answer is right now not at all, because we've just started doing it. But we're literally in the process of. So if you can see that we took extreme cases. We took extreme cases here, so like the max and the min, and we're right now in the process of looking at taking cases in between. So say 35% porosity, where we've trained on 20 and 50. And doing comparisons, so all of the comparisons that we would normally do, and say how realistic does our interpolation look compared to experiment. But there is a fundamental issue here of how we control that interpolation, because there's no real direct way of there's no way of really conditioning your GANs to understand how to interpolate. So that is a challenge. The question about whether an optimum lies in between these values, we can look at, I think it's definitely a fair question in that we don't know whether an optimum lies in between those values. But when you're exploring, say, 16 parameters, and we're largely constrained by manufacturing, we're constrained in some cases by manufacturing constraints. In some cases, we're constrained by just what we know in terms of is a realistic range for, say, particle size distribution. So there are a bunch of different constraints that we can say, this is a realistic area to explore. And on top of that, when you're exploring 16 parameters, you can explore 8, 10, 16 parameters at the same time. We're likely to find some interesting results, even if we find that the optimum is on the edge of some parameter, we can take it, we can train a new GAN where we explore off into that direction. So if you're coming to, if we have 20 and 50% porosity that we're trained on, we find 20% as optimum, make a new image with percent porosity, try it again, and that will be a legitimate stage of that process.
Fantastic. We do have another question. This is from Billy Wu. Great talk, Steve. How resilient is the output to input artifacts? For example, if there is a contrast gradient charging in the input SEM image, would this impact the output structure?
It depends how large your image is and how statistically significant that artifact is. As in, if you have a single artifact, then you may see that however common your artifacts are, that is how common they will be in your output data set. The whole idea is that we capture a distribution of features, and if an artifact is a feature, it will be captured. So the idea that we need a realistic training image is definitely true, but that is kind of the case no matter what simulation you're trying to do on microstructure. We always have to deal with artifacts. You're always going to have to try and clean up an image after, you're always going to have to do some post-processing. And essentially the fundamental thing is that whatever quality your image is, that's the quality that your synthetic samples will be. But that is fundamentally why in all of these images we use segmented images where there has been post-processing to say, we only have 3 phases, it has to be one of those 3 phases. We're not using like a grayscale image for that very reason, to try and avoid artifacts. Cool.
Perfect. Thank you very much. Thank you very much, Steve, for such an informative presentation, and also through getting through so many questions. So a recording of this webinar will be put up on the IMSE YouTube channel very soon. You can find a link for this in the chat function. The next webinar in this series will be on the 8th of October at 2 p.m. and that will be on the theme of understanding the factors governing the performance for garnet electrodes in lithium metal batteries, and this will be presented by Dr. Ariana Agudero and Federico Pescici. So I just want to say thank you again to Steve and for everyone for joining us today. I hope you all have a nice day. Thank you very much.
Cheers.
Bye.